In this video, we will talk about the one-sample t-test. The one-sample t-test is not something we usually need to do very often, but it acts as a conceptual bridge between things we've already talked about and things that are coming up that are very useful and very frequently used. In fact, we have already done, in a way, the one-sample t-test, but we haven't called it that. So let's see what it is about. The t-test is a hypothesis test. The hypothesis we test with the one-sample t-test is that the mean is not equal to a specific reference value of interest. So there is a value that we wonder about. We have a sample, and we want to know if this sample is consistent with sampling from a distribution with that reference value as a mean. The null hypothesis is that the mean is equal to that specific reference value. So if the mean of the population we're sampling from is equal to that reference value that we specify, then that would be a true null hypothesis. To be equal to a reference value is the same thing as saying that there is a zero difference between the mean and that reference value. So the null hypothesis does indeed concern a zero, but it's a zero in the difference between a value that we specify and the mean of the population we're actually sampling from. In other words, one way to state this is whether our mean is different from a reference value or whether we are sampling from a population that has this value as the mean. These are two ways of stating the same thing. This has been a bit abstract, but it will become more concrete in a moment. Just bear with me. Let's go back and remember momentarily our discussion of the standard error. That was the case where we had a population with a population mean of 175 and a standard deviation of 10. And this was a hypothetical population with measured heights, so people's heights in centimeters. And by repeatedly sampling from this population, we came up with a bunch of samples with different sample distributions, and then we calculated their means, and this was the distribution of the means of the different samples. And now we know that this is the sampling distribution of the mean, and we also know that the mean of the means, so the mean of this distribution of the means of all the samples, is equal to the mean of the population. So if you have very many samples, the mean of their means will actually tend to the population mean. And the standard deviation of this set of means, of sample means, is related to the standard deviation of the population by dividing by the square root of the sample size. So larger samples lead to smaller standard deviation for the sampling distribution of means. Now this is all good and true and completely theoretical. We never know the population values. That's why we do studies with samples, and we never actually sample thousands or millions of times. So this is just a theoretical background that informs us what the sampling distribution of the means is like. And that's important because our mean must be one of these. So we learned something about its properties. So let's forget about this theory and go back to reality. In reality, we don't know this part. We don't even know if our sample really comes from this population. If we have a sample, one sample in our study of 25 people, we measure their heights, and we may ask, does our sample come from this population? What does this mean? This is another way to ask whether our sample is consistent with a population mean of 175. So this particular random sample happens to have a sample mean of 176.56 and a standard deviation of 7.44. It's just a random sample. So it is actually some distance from this population mean, but remember, we don't know this, and we don't even know for sure that our sample values are consistent with this population because we don't know this. We just have a group of people, we've measured their heights, and we want to know if they come from this population or not. The standard error of the mean is equal to the standard deviation of the population divided by the square root of sample size, so it would be equal to 2 in this case. Our mean is 176.56. This is for our one and only sample. And we want to compare our mean to the reference value of our question. Our question is, does our sample come from a population with population mean equal to 175? So how far from that reference value are we? Well, we have to subtract this from our own mean. 176.56 minus 175 is 1.56. This is how far we are from our reference value. Our sample mean is 1.5 centimeters away from our question, our reference value. If we divide this distance, this is a distance in centimeters, so in the measuring units, if we divide this by the standard error, then we find that we are 0.78 standard errors away from our reference value. However, you should by now have realized that we can't do this because we don't know the actual standard error of the mean because we don't know the standard deviation of the population. All we have is our sample. So this doesn't exist. And these do not exist. What we do have is our estimate for the standard error, which is the standard error of the mean from our sample, which is equal to the standard deviation of our sample divided by the square root of our sample size, and that's 1.49. This is our estimate for the standard error of the mean based on our sample, and is affected by the fact that our estimate for the standard deviation may be a bit off from the actual standard deviation of the population. But anyway, these are the only numbers we have. So then what we can do is we can divide the distance between our mean and the reference value, divide this by our estimate for the standard error of the mean, which we do have based on our sample standard deviation. The difference or the distance between our sample mean and our reference value divided by our estimate for the standard error. This is called the t-value. The t-value for this problem is equal to 1.05. If we substitute the numbers we have for our sample mean, for the reference value we are asking the question about, for the sample standard deviation and the sample size, we come up with a t-value of 1.05. What is this t-value? It is a standardized distance. It is how many standard errors away from the hypothetical reference value our sample mean lies. So the t-value here says that our sample mean is 1.05 standard errors away from the hypothesized reference value of 175. We are 1.05 standard errors away from this one, And our standard errors are calculated based on the standard deviation of our sample. So there is an uncertainty there as well. Now, what can we do with this t-value? As you recall, the number of standard errors is associated with probabilities. So if we go back to the normal distribution, we know that 95% of means will lie within 2 standard errors from the population mean. So 0 would be a distance equal to 0 from the population mean. 95% of sample means lie within 2 standard errors. And this means that 5% of means lie outside of 2 standard errors. And there are more pairs like that. In fact, we can come up with any numbers we want and look up the corresponding values for the normal distribution. And these are the fixed values, the rough values we have to remember because they're very useful for quick judgments. And for example, we know that a range of plus or minus 2 standard errors is associated with 95% of values within that range and 5% of values outside that range. And we know that these are approximate numbers that we can easily remember, and we can look up the actual values for these proportions, and it just turns out that for 95%, the 95% of means lie within 1.96 standard errors actually. Not exactly 2, close enough. But this only holds for the normal distribution. Our t-value is not normally distributed because our estimate of the standard error includes an uncertainty in the computation of the standard deviation, which comes from the sample. So it is subject to uncertainty in the same way that the mean of the sample is. This means that instead of looking up the corresponding proportion in this curve, which is the normal curve, we have to look it up in a t-curve, which is very similar. Look again, this is the normal curve, and these are some t-curves. You can see that the light blue t-curve, which corresponds to 100 degrees of freedom, is essentially on top of the red curve. So with lots of degrees of freedom, the t-curve tends to the normal curve. But for fewer degrees of freedom, we see that there is a difference, which is most visible in this region. So there is extra uncertainty farther from the mean, especially with very few degrees of freedom. In practice, all this means is that instead of looking up the proportions in the normal distribution, we'll look them up in the t-distribution. So these numbers change by changing the lookup. And if we were looking up for 10 degrees of freedom, it turns out that 95% of t-values lie within 2.228 from 0. So from minus 2.228 to plus 2.228. That includes 95% of values, and therefore 5% are outside. If we look up with 100 degrees of freedom, then the corresponding value would be 1.984. So with 100 degrees of freedom, 95% of t-values lie within minus 1.984 and plus 1.984. What are these degrees of freedom we're talking about? As we've also seen in the context of the chi-square analysis, degrees of freedom have to do with how many values are free to vary, or conversely, how many constraints there are on the values. In our hypothetical example, with a sample size of 25, there are 25 data points. But in order to get to the t-value, we had to calculate a mean. And to calculate a mean, we had to sum up all the data points before we can divide them by how many they are. So this calculation of the mean by summing up creates a constraint. This means that the sum cannot change once it is calculated. So if 24 of the 25 values vary, the 25th must vary to compensate for all the other changes. So the 25th value is not free. It is constrained by the sum to change in accordance with any other changes. So you only have 24 free values, and that's 24 degrees of freedom. In other words, calculation of this one mean removes 1 degree of freedom from the sample size. In general, for the one sample t-test, where we need to calculate one mean, the number of degrees of freedom is n minus 1, so one less than the sample size. This is the general rule for the one sample t-test. So now we have all the information we need in order to look up the corresponding value. If we go to the p-value app and enter the t-distribution, the number of degrees of freedom, and the value of our t-statistic that we calculated, that 1.05, then we get the answer that the p-value is 0.304. This is the proportion of t-values with 24 degrees of freedom that lie outside of the range from minus 1.05 to plus 1.05. So the two gray areas together add up to 30.4%. And so there is a 69.6% within this range. So this is our p-value, and it is greater than our alpha level, whatever our alpha level is. It's not going to be 0.3. If we use the conventional alpha level of 0.05, we can see that this p-value is much greater than that. Therefore, we cannot reject the null hypothesis. Which null hypothesis can we not reject? We cannot reject the null hypothesis that the difference of our mean from 175 is 0. In other words, our data are consistent with sampling from a population with the mean of 175, our hypothetical reference value. This is the one we asked about. So our sample is consistent with this. Another way to state it is our sample mean, which was 176 point something, whatever it was, it is statistically indistinguishable from 175. The way to report this result, according to the APA style, is this one. And you have to be very careful in typing it exactly, including where there are spaces, where there are no spaces, where there is a comma, when there is a digit before the decimal point, and when there is none. The T and P are slanted, so they're italic font. Then there are no spaces, and here we note the degrees of freedom for the T distribution that we used. Then equals to whatever our T value is. We usually don't need more than 2 decimal places. So get into the habit of reporting 2 decimal places for statistics, with the exception of the p-value, where we usually use 3 decimal places. And the p-value is reported without a leading 0 because probabilities can only go from 0 to 1. So numbers such as the p-value that never exceed 1 are reported without a 0 before the decimal point. As you've probably noticed, none of the steps we took here are new. We have used these same concepts and same calculations when we computed margins of error and confidence intervals. And we used the same concepts from the sampling distributions, in particular, the sampling distribution of the mean. And the fact that using the sample standard deviation introduces uncertainty that is accounted for by looking to the t-distribution instead of the normal distribution. The only thing that is different today is that we have recast this as a hypothesis test, and we have given it a name, namely the one sample t-test. Let's do another quick example just for a little extra practice. Imagine that we had a sample with a mean of 166 and a standard deviation of 15. Can this sample have been sampled from a population with a mean equal to 175? Well, we can run our t-test. We have to subtract the reference value from our mean and divide by the estimated standard error. So 166 is our sample mean. Subtract our reference value, the question. Here is our sample standard deviation, and here is our sample size. And the answer here is t equals -3. So we are 3 standard errors away from our reference value. And because it's a minus, it means we are 3 standard errors below, not above, the reference value. The negative sign indicates that our sample mean lies to the left of the reference value. If this were positive, we would be to the right. Looking up the probability associated with 3 standard errors away from the reference value for a sample size of 25, that is 24 degrees of freedom, gives the answer of 0.006 for the p-value, and this is how it would be reported. In this case, we have to reject the null hypothesis. This sample, a sample with a mean of 166 and a standard deviation of 15 with a sample size of 25, is not consistent with sampling from a population with mean equal to 175. This does not mean that it's impossible to get it from this population. Indeed, it is possible with a 6 in 1,000 probability. When we say it's not consistent, this reflects our criterion for rejecting the null hypothesis. So if the p-value is less than alpha, we conclude that our sample does not come from this population by essentially saying that this is such a low probability that we prefer to not consider this hypothesis and to reject it. And so conclude that our sample must in fact have come from a different population. This was the one sample t-test, and once we understand this process, then we're ready to move on to the much more frequently used independent samples and paired samples t-tests.